Continuing with the basic foundations of the processes we are interested in, hydrostatic balance is very critical in the vertical. In the horizontal, we keep talking about geostrophic adjustment, and we said extratropics, mid-latitudes are essentially in geostrophic or quasi-geostrophic adjustment balance, with Rossby number being much less than 1. As you come into low latitudes, obviously Coriolis becomes weaker, going to 0 on the equator. Hence, geostrophic constraint is going to be weaker as well. So when we say geostrophic adjustment, essentially we are going to look at a system that is in geostrophic balance and then look at how a perturbation to the system will influence the return of the whole system back to geostrophy, right? For that, we will need the concept of Rossby radius of deformation. We will see that this is a well-defined quantity associated, named after Rossby, the king who discovered so many things. For a shallow barotropic fluid of depth h, we will simply jump and write it as c over f, where c is the gravity wave speed. Again, remembering gravity is the restoring force in that case, one of the fast waves in the system, divided by f, which is the Coriolis effect. And for a shallow water, gravity wave speed is just square root gh. So it's square root gh divided by f, where h is the scale height of or the equivalent depth of the flow we are looking at. This becomes a problem for the ocean, as we will see, because ocean is several kilometers deep and it's stratified, so we'll have to do some fancy arguments which are very valid. In a baroclinic fluid, then C over F can be written in terms of Brent-Vesala frequency and the scale height, G. Okay, go back to the table and look at the definitions. I won't repeat them here, but as I said, always keep the table handy. So this then leads us to the so-called inertial motion. What is inertia? Basically, it's your ability to resist perturbations in a simple sense, right? So if you are an adult with a certain weight and the child is pushing you, you are very unlikely to budge. But if you push the child is going to keep going, and how far the child will go will depend on inertia. Silly example, don't push kids. Okay. In the real world, on a rotating planet, winds can kick off, let's say, a parcel of water by a burst of wind, and then winds die down. Then it's important to see what happens to that parcel of water if there is no friction to dissipate the motion. That's essentially inertial motion. Obviously, we will immediately combine it, saying when there is free motion at planetary scales, Coriolis will be there. So Coriolis is going to push things to the right of the direction of motion in the northern hemisphere and to the left of the direction of motion in the southern hemisphere. And it turns out that the inertial motion in both hemispheres then always turns out to be anti-clockwise or anticyclonic. Okay, for a flat ocean with no pressure gradients, so let's assume the entire planet is an ocean and it has no pressure gradient to start with. Look at our balance. So the acceleration term is going to just be balanced by the Coriolis term, because we have assumed that there are no pressure gradient. So in that case, v is just dy dt, the time rate of change in the latitudinal direction. dv dt is minus 1 over rho dp dy. dp dy is going to go to 0 and minus f times u, and this is just going to become f times u. That's minus missing there, another typo. So that's going to be minus f times dx dt, the longitudinal change in time. Very simple system. Then in this case you can write u as a function of y plus u as a function of y plus some constant, and v as a function of x plus a constant. You can easily write u squared plus v squared as a constant because a and b are also constants. Right there, you can take these and do x squared plus y squared and all those good terms, where u and v are x minus b over f squared plus y plus a over f squared equals c squared over f squared. It's a fancy way of producing a circle. Essentially, if there is a burst of wind and the ocean water is set in motion and the wind dies away, which actually happens a lot, then the water can keep moving in a circle because of Coriolis balancing the inertial motions. Also happens in the atmosphere, but atmosphere moves fast. It's got rapid motions and lots of things happening, so not very easy to detect inertial circle, but in the ocean it's fairly easy to detect them. So a radius of r given by c over f and centered at b over f and minus a over f is produced, and the inertial scale is proportional to 1 over f, and we already know that f is dependent on latitude, going from 0 to the maximum at the poles. So the inertial scale is going to decrease as f increases. Inertial, obviously this becomes infinity at the equator. Inertial period can be computed as 2 pi c over f divided by c, and that can be written as pi over omega sine f, which is our local vertical component, so that's 2 pi over f. I'm just running through them because this is fairly straightforward manipulation of the equations. So the time scale that emerges a period is 2 pi over square root zeta plus f times f, where now we are back to the total vorticity of the fluid parcel itself. So that will be 2 pi over square root eta f. Okay, so we can look at inertial periods in days of the ocean and the atmosphere as a function of latitude. The Rossby radius of deformation is going to depend on the equivalent depths, the depth that the forcing is going to see, essentially where the motion drops off by 1 exponential. So if force at the surface is going to drop off by 1 exponential because of the effectiveness of the penetration of the momentum from the wind into the ocean, which we will see in a minute. Atmosphere relative to equations 3.34, which you look up ocean using equation 3.34, but with reduced gravity, because we will see that in a minute as well. The water buoyancy is going to depend very much on the water below, plus water is several kilometers deep. It's very hard to explain the motions if you assume equivalent depth of several kilometers, other than the tsunami, which moves very fast, faster than a jet. It's as a shallow water equation. In case you don't know what shallow water waves are, shallow water wave, not equation. A wave that feels the bottom is a shallow water wave. A deep water wave is which doesn't feel the bottom. So H becomes very critical for the ocean. We will see that because ocean is stratified, you can assume the water column above the thermocline as the equivalent depth. So here are the periods at different latitudes, going from 5.6 to 0.7 in days. Atmospheric Rossby radius of deformation, which we will define in a minute again. We already defined it as square root gh over f. Obviously, wave speed is going to determine that as well. And that's going to depend on the equivalent depth. You can see that as equivalent depth increases, square root gh increases, so the Rossby radius of deformation increases, and f increases as you go to higher latitudes, so the Rossby radius drops off. Similar things for the ocean. With latitude, drop in the Rossby radius of deformation for the same equivalent depth, and the Rossby radius increases with the equivalent depth. Okay, these are the adjustment problems that we will discuss. We'll continue this in a minute in terms of inertial motions, but I hope you got a sense. We will see some figures that will make it clear that inertial motions are very important in the ocean, in the atmosphere. Not easy to detect, but they do exist.